All right, so the last time we discussed this idea of persistent homology, so now we're going to talk a little bit about how you go about actually computing it in practice. Um, and as we saw before, it's like when we're talking about homology more generally, we saw that there was a way to do some sort of matrix reduction on the matrix which represents the boundary operator. And doing this allows you to then compute the Betti numbers in some way, shape, or form. So what's perhaps interesting for persistence is that it turns out you're able to do this sort of all at once. And so let me say a little bit about how you go about doing this. So this is matrix reduction, sort of for sort of persistent homology. Okay. So the first order of business is to look at how we're going to represent this boundary operator. And as I sort of alluded to, what we're going to do is we're going to basically combine all the individual boundary matrices, it's like for all simplices of different dimension, into a single boundary operator. So that's one thing. And the other thing is that this involves a particular ordering of the simplices. Which we'll talk about in a little bit. Okay, so we're going to combine sort of all the boundary operators into a single matrix. Okay, and so in particular, this involves, it's like all the sort of nested simplicial complexes and sort of all simplices of different dimensions. Okay, so this involves sort of ordering sort of all the simplices in a particular way. Okay, so there's this idea of what we're going to call a compatible ordering. Okay, so we refer to this as a compatible sort of ordering. Okay, and in some sense, what's going to happen then is that if you sort of truncate, it's like this enumeration of the simplices, it's like at any point, you're going to get a subcomplex of the containing simplicial complex, and it's also sort of going to respect the filtration property, if you will. Okay. So, all right, so refer to this as compatible ordering. It's like of simplices, let's call that sigma 1 to sigma m, okay, and with the property that, okay, so such that if, for example, I is less than j, right, then the filtration function you apply, it's like to sigma I is going to be less than sigma j. Okay, so that's one thing, and it has to be that even if they were equal, okay, so that's the possibility that it's like these things are equal, then they has to be ordered. It's like in sort of increasing order of sort of faces, if you will. Okay, and if sort of sigma I is a face no, I'm sorry, that's not what I meant. Okay, so what I meant was that okay, so the implication is a little bit different. Okay, so what it says is the following. So if the filtration function applied to sigma I is less than the filtration function applied to sigma j, then it has to be that I is less than j. All right, so that means if the value associated to sigma I is less than the value associated with sigma j, it's like then sigma I has to appear earlier, it's like in the sequence, okay? And then the second thing is that, you know, if sigma I is a face of sigma j, and again, it's like sigma I has to appear earlier, it's like then sort of sigma j, it's like in this sort of ordering, it's like of the simplices, okay? And so the idea then, again, as I said, is that if you were to truncate, it's like this sort of enumeration, it's like the simplices at any point, you would get A as like a simplicial complex, and then B, it's like it would be compatible with this filtration. Okay? All right. So, and then, so such an ordering exists because F is monotonic. Okay, and then essentially what I had said before is that sort of every sort of initial subsequence of simplices form a subcomplex. Okay, so again, it's like the idea is that if you sort of go through this enumeration and you truncate it at any point, it's like then the stuff, it's like which you didn't sort of discard, it's like would form a subcomplex of the full simplicial complex of K, right? All right. And so now what you can do then is that you can define the boundary operator for this particular ordering of the simplices, okay? So again, normally it's like when we talk about boundary operators in the context of homology, we think of breaking them up sort of by simplices of the same dimension, but nothing really prevents you from sort of just collecting all that information into a single matrix. Okay, so you have simplices from 1 to m, right? So the boundary operator associated with this sort of enumeration of the simplices then is an m by m matrix, right? So we construct a sort of m by m sort of boundary matrix. Let's say boundary, okay, which stores all the simplices of all dimensions in one place, right? And then the idea, of course, is that we're going to do some sort of reduction. It's like on this m by m boundary matrix, okay? And in addition to that, you know, the reduced version of this is going to then give us some information. It's like about the persistent homology. Okay, so so let me define. It's like what the entries of this matrix boundary ij. So this is the ijth entry of this boundary matrix, right? So this is just one, right? If sigma I is a codimension 1 face of sigma j, so that just means that sigma I is a face of sigma j and it has dimension 1 less than sigma j, okay? And then it's 0 otherwise. So again, it's easy to convince yourself that this is really nothing more than what we would normally have. It's like we had sort of combined all the boundary matrices together. So in particular, if instead of this notion of compatible ordering which we had sort of ordered the simplices by sort of dimension, right? So starting with the zero-dimensional sort of simplices, the zero-dimensional nodes basically, all the way up to the highest dimensional simplices, then what would happen is that this boundary operator, it's like with respect to that different ordering of the simplices, would just be blocks which correspond to the individual boundary operators, right? So that's sort of easy to convince yourself of. Okay, so well, maybe you want to order it from the highest dimension to the lowest dimension, but it's like there's a sense in which this boundary operator is again encoding all the information which the individual sort of boundary matrices sort of created by dimension is encoding. Okay, all right. So so what this means is that so the rows and columns are ordered. It's like according to this compatible ordering, right? So rows and columns ordered by the compatible ordering. And the boundary of a simplex is recorded in its column. Okay. So what you're going to do basically is to then do column operations on this boundary matrix. Okay. And the way again to think about this is that when you sort of add one column to the other, then what you're going to do is that you're going to represent the boundary of the sum, it's like of those two simplices, right? And then more generally, it's like the columns will actually represent chains. Okay, once you've done a few of these column operations, right, and then the column associated with that chain obviously is the boundary associated with that chain. Okay, so that's basically where we're headed with all of this. So let me just state what these reduction procedures are going to do. So as I said, the algorithm uses sort of column operations to reduce the boundary operator, the boundary matrix to another sort of matrix with just 0, 1 entries. Let's call it R, which is stands for reduced. Okay. And then we're going to define something that's like on this matrix R. So so let low j, right, be the row index of the lowest one in column j. Okay, and then so this is just something that's like which takes a number j. It's like, and it looks at column j, and then it tells you what the position. It's like the row. It's like index of the lowest one. It's like in that column is. Okay, so if the entire column is 0, right, then low j is undefined. Okay, all right. Let's see if I can get a pen which works better. All right. Okay. And then, all right. So then we'll see something about what it means for this matrix R to be reduced, right? So we call R reduced, right? If sort of low j is not equal to low J0 whenever J and J0, right, and in particular where J is not equal to J0, right, correspond to sort of two non-zero columns. Okay, so basically what you want is that if you have two non-zero columns, then it has to be that the lowest non-zero entry, okay, which is then defined because they're non-zero columns, right, is not equal to each other, again, unless the columns are the same. Okay, all right. All right, and then the point, if you will, is that we'll introduce an algorithm. It's like which will take the boundary matrix sort of boundary, okay, and then convert it. It's like into this sort of reduced matrix with this property, okay. And we're going to do this. It's like through column operations where you take columns from the left and you add it to the right, okay. And I'll say a little bit about why you do the left to right thing. And it has to do actually with the structure, it's like of the boundary matrix. When you have a compatible ordering, it's like of the simplices. So, so we reduce boundary to R using column operations where we add columns from the left to the right. Okay, so one thing which you observe is that you recall there were two conditions for the idea of a compatible ordering, one of which has to do with the filtration function, and then the other one has to do with the idea that if a simplex is the face of another simplex, then it somehow appears earlier. Okay, so a consequence of this second property is that when you write down this boundary matrix with respect to compatible ordering, that boundary matrix is going to be upper triangular. Okay, so a consequence of ordering the simplices so that the faces appear first, if you will, is that the boundary matrix is upper triangular, right? Okay, so that's an observation. Okay, and then of course the other observation is that if you only operate, it's like on this matrix through column operations where you add a left column, it's like to a column to its right, right? Then you also maintain this upper triangular structure, right? So this is preserved when sort of adding columns from the left to the right. Okay. All right. And then you probably already know that row operations can be thought of as a linear transformation or as a matrix acting. It's like on another matrix on the left, and then it's like column operations are related to multiplication, it's like on the right. Okay, so what happens then is that you start with the boundary operator, or the boundary matrix, and then you perform these column operations so that you end up getting this reduced sort of matrix R. Okay, so we're going to get R is equal to the boundary operator times some sort of matrix here, again upper triangular as it turns out, right, because you're only adding again left to right. That will again, it's like give you these kind of column operations. Okay, so so R is some upper triangular matrix, right, which is related to some boundary matrix, then multiplied by some, again, upper triangular matrix, which represents the column addition action. Okay. So the white part here are all going to be necessarily zeros, and then the part which is shaded in could be 0 or 1, depending, but aren't necessarily 0. Okay, so that's all we were saying. It's like when we shade that in that way. Okay, so that's basically what you're going to try to do. Okay, and let's sort of discuss the algorithm. It's like for taking the boundary matrix and then giving you this reduced matrix which satisfies that condition on the lowest one in the column. Okay, all right, so let me give you the algorithm for that. So sort of the matrix reduction algorithm. Okay, so you start with R is the boundary operator, the boundary matrix, I'm sorry. And then, if you recall, there were m rows and columns, right? So you go one by one. For j equals to 1 to m, you do the following. All right, so while, so basically you keep doing this while the matrix is up to a point is not in reduced form, right? So while there exists some j0 less than j, where sort of the lowest one of j0, right, is equal to the lowest one of j, you do the following. Right, so that's the condition. It's like you want to avoid, right? You want to avoid the condition that you have non-zero columns, right? Two non-zero columns. It's like such that they have the same, it's like row. It's like where the lowest one occurs. Okay. So if that happens, it's like then essentially what you do is you add. It's like the column j0 to column j, and of course you know that what that will have the effect of doing is that you're in, it's like z mod 2 z coefficients, modulo 2 arithmetic. So adding 1 to 1, it's like gives you 0. So the act of adding sort of column j0 to column j is to essentially get rid of the 1, right, in that position, in the low j position. It's like in column j. Okay. All right, so you do this. You add column j0 to column j. Okay, and so that will have the effect of making these two different. Okay, after this operation. Okay, so you end the while, and then you end the for statement. All right, so that's a very simple kind of algorithm. All right, and right, so okay. So as I said, it's like the net effect of this operation, right, is to have a bunch of column additions. It's like where you take one column, you add it to a column on the right. Okay, and this can be represented, it's like by multiplying this boundary matrix delta, it's like on the right by some matrix V. Okay, all right. So, and again, as I said, what happens is that delta, right, because of this compatible ordering which you choose, is an upper triangular matrix, right? And then, of course, adding, it's like a column to its right, okay, is also going to, it's like maintain the upper triangular structure. So, R is upper triangular. And then it's like you can convince yourself that the operation of adding one column, it's like from the left to a column on the right, is represented by a upper triangular matrix. Okay. All right. So and that the upper triangular matrix is acting, it's like on the boundary matrix on the right. Okay, so that it acts on the columns. Okay. All right, and then so you sort of, in any case, it's like you end up with this sort of very simple algorithm. All right, and here, of course, we're only sort of operating, it's like on R. Okay, but if you wanted to sort of know what V is, it's like you can in this operation you can sort of add to this part an update for what V is, right? So if you wanted to augment this, for example, it's like you would have R equals to the boundary, and then V would start off with the identity. It's like, and then you would sort of update V. It's like by sort of remembering what column operations you were applying to the boundary, and sort of just keep track of that. And so here it's like you could update that V from the identity to whatever ends up transforming the boundary matrix to R. Okay, so I won't go into those details. It's like, but that's something which one can keep track of as well. So in any case, once you have this algorithm, right, then there are some observations you can make. So once you get this into reduced form, the claim is that you can then extract information about the persistent homology. Okay. So to get the ranks of the homology, well, I should say that right now it's like this just gives you the actual homology. Okay, but we'll see how you can actually extract the persistent homology in a little bit, and it has to do with the significance of these lowest one values. Okay. All right. So to get the ranks of the homology groups of K, okay, what you do is that the number of 0 columns that correspond to P simplices, right, is the rank of the cycle group ZP. Right, so that maybe is worth thinking about for a second, right? So if you look at this algorithm, again, it's like, if you think about it, when I say that low J0 is equal to low J1, what that's really telling you, if you will, is that, the column J0 and column J1 correspond to simplices, and then more generally, after a few iterations of this, chains which have the same dimension, right? And it again has to do with the fact that, it's like if there's a one entry there to begin with, it's like in the boundary map, right? It basically, and they correspond to the same thing. It has to be that the dimension of, again, the chains associated J and J0 are the same as well, right? So, and so in some sense, when you do these column operations, you're mixing simplices, but you're not mixing the dimension of the simplices, right? So it respects the sort of the grading. It's like coming from the dimension when you do these column operations. Okay, so the point then is that these columns, right, retain the property that is a well-defined dimension associated with each of them. Okay, So anyway, so then it makes sense to talk about, the looking at zero columns, which corresponds to p simplices. Okay, all right. So, all right, and then similarly, sorry about the ink. So similarly, right, the number of non-zero columns give the rank of the boundaries. Okay. And then, of course, it's like the Betti number is the difference of these, right? And then the difference is the Betti numbers. And I'll just say the difference is the Betti number. Okay, all right. So that sort of tells you how you can construct this matrix, which encodes the entire sort of boundary operation at all dimensions, and that you have a matrix reduction algorithm which operates on all dimensions at once, but because of this sort of property that you only get non-zero entries, it's like in the same row, it's like if the associated columns have correspond to simplices of the same dimension. Okay, these column operations respect this grading. It's like of the simplices by dimension, and so you can still think of each of these columns as corresponding to chains of a particular well-defined dimension. Okay, so it's like even though you're doing all these operations at once, it respects this ordering by dimension, and so you can extract the relevant sort of ranks. It's like of the cycle and boundary groups, and from this sort of single reduction process, and then of course the difference is the Betti number. Okay, so let me just stop here for now.